Welcome to the Deep Dive, where we plunge into the heart of what's shaping our world. The tech landscape is always morphing, constantly evolving, and a lot of that incredible change is powered by specialized hardware humming quietly behind the scenes, stuff most of us never even think about. But this silicon, the very brains of our devices, it's getting smarter, more adaptable, and, well, way more specialized. Today, we're pulling back the curtain on one of the most fascinating pieces of this puzzle: field programmable gate arrays, FPGAs. These aren't just another chip, they're something truly unique. Our mission for this deep dive is to explore whether FPGAs are destined to remain, a niche technology, a specialized tool for specific tasks, or if they are maybe on the cusp of becoming mainstream, like an indispensable component in an increasingly complex computing landscape. And here's a little hint: the answer probably isn't about FPGAs replacing anything. It's more about them becoming a crucial complement, like a brand new kind of computing. Okay, let's unpack this then. Before we even talk about the future, maybe for those less familiar, what exactly is an FPGA at its core? And what makes it so fundamentally different from, say, an ASIC, an application-specific integrated circuit?
Yeah, that's definitely the best place to start, because understanding what an FPGA is, it really helps us understand its journey, its potential. So at its heart, an FPGA is unique because it's essentially reconfigurable silicon. Imagine a piece of hardware where you can actually change its internal wiring and functionality after it's been made, after it leaves the factory. That's kind of the magic.
Okay, reconfigurable, so you can change it later.
Exactly. Now, contrast that with an ASIC. An ASIC is, well, it's custom designed for one single fixed purpose. Think of it like a perfectly crafted sculpture, but it's unchangeable. Once it's made, that's it. An FPGA, though, it offers this really critical ability to update its functionality or even fix bugs, after it's been deployed out in the field.
Wow, okay.
Which means it can adapt to new standards or new algorithms, maybe even entirely new applications, all without needing a physical hardware replacement.
So it's like a chameleon chip almost in the silicon world.
That's a great way to put it, yeah. A very smart chameleon.
So historically, how did that incredible flexibility position FPGAs in the market? Because, for a long time, they've definitely been seen as a distinct specialized tool, right?
Exactly right. That inherent flexibility, it historically carved out a very distinct, although quite profitable, niche for FPGAs. They became the go-to for things like low-volume production runs, rapid prototyping, and a lot of research and development. Think about areas where the super high non-recurring engineering costs the NRE and the really long design cycles of ASICs were just, well, they're prohibitive.
Right. Building an ASIC isn't cheap or fast.
Not at all. It's like building a custom factory just for one specific product. It really only makes sense if you're going to make millions, maybe tens of millions of them. For FPGAs, the value proposition was different but clear. You paid a higher cost per chip, but in return, you got vastly lower NRE and, crucially, that superior flexibility. It was a trade-off, and that defined their role for decades.
And what's fascinating here is how that fundamental set of trade-offs, how they stack up against other computing architectures we might be more familiar with, like CPUs, GPUs, ASICs. Where do FPGAs really fit into that bigger picture, thinking about purpose, performance, flexibility?
Yeah, if we sort of lay out the landscape of processors, you see these really distinct roles emerge. CPUs, they're your general purpose workhorses, right? Great for sequential tasks, running operating systems, that kind of thing. GPUs are the masters of highly parallel computing, think graphics, obviously, but also increasingly certain types of AI training. ASICs, as we said, are the ultimate specialists, peak performance, peak efficiency, but for just one fixed function. FPGAs, though, they sit in this really unique spot. They offer highly parallel processing, but for custom logic. And the crucial part, the reprogrammability.
Okay, so performance-wise, where do they land in that hierarchy?
Performance is interesting. ASICs are usually top tier for their specific task. Then GPUs, because of their sheer parallel power for certain workloads. FPGAs offer high parallel performance, but it's very specific to the tasks they're configured for at that moment. But flexibility, that's where FPGAs really shine. They're highly flexible.
Much more than the others.
Oh, yeah. ASICs have basically zero flexibility post-manufacturing. GPUs have some, medium flexibility through programming. FPGAs are designed for it, and time to market. FPGAs are fast. We're talking months, typically. ASICs could be years.
Right. Those trade-offs are so key. Now, I've heard terms like spatial parallelism versus temporal parallelism come up when people talk about FPGAs. Can you maybe break down that technical differentiator for us? How does an FPGA actually achieve its performance differently?
Absolutely, and it's really a critical distinction to understand. So a CPU typically executes instructions sequentially, one after another. Maybe it does a few at once with modern techniques, but fundamentally it's processing over time. We call that temporal parallelism. It's slicing tasks across time.
Okay, time-based.
Right. An FPGA, however, it does something fundamentally different. It actually builds the instructions directly into the hardware. It creates custom digital circuits on the fly, configured to execute multiple operations simultaneously. This is known as spatial parallelism. It's using the chip space to do many things at once.
Ah, okay, so it physically lays out the task in hardware.
Precisely. And this unique approach allows FPGAs to achieve really significant performance gains for specific parallelizable tasks, sometimes even at a lower clock frequency than a CPU, because they're doing so many things at once, perfectly configured for that one job.
Interesting. And what about power consumption? That's always a big factor.
Yeah, power's a mixed bag, but generally favorable for specific tasks. FPGAs can be significantly more energy efficient than CPUs or GPUs for those targeted active tasks. You could look at it on a power per operation basis, and they often win. But there's a caveat. The very thing that makes them flexible, the programmable interconnects, the configuration memory inside that stuff, consumes considerable static power. Just sitting there, it draws power.
Even when it's not actively computing something.
Exactly. That's less of an issue for an ASIC, which has fixed, optimized circuitry designed to be lean for its specific task.
Makes sense. And you mentioned the economics, the NRE costs for ASICs running into millions.
Millions, yeah, sometimes tens of millions, especially for cutting-edge process nodes. It's an investment only justified by extremely high volume production. But here's the interesting part, the trend. The cost of ASIC development keeps rising with each new, smaller manufacturing process node. This actually pushes that economic crossover point higher.
Meaning FPGAs start looking better for more projects.
Exactly. It makes FPGAs a more attractive option for a wider range of projects that maybe don't need those absolutely massive ASIC volumes, but still need custom acceleration. And finally, just to reemphasize that unparalleled flexibility and fast time to market, the ability to quickly implement, test, and crucially update designs in the field is just essential in fast-moving sectors. Think 5G telecommunications, autonomous vehicles. Standards are constantly evolving there.
Okay, so FPGAs clearly have this incredible flexibility, this unique way of processing. But as we said, they've largely been a behind-the-scenes hero. We're talking about them potentially going mainstream. But what does mainstream even mean for a technology like this in today's super diverse tech world? It's probably not about, like, everyone having an FPGA in their phone next year, is it?
You're absolutely right. Mainstream here doesn't mean what it used to say for the CPU. It's not about ubiquity in every single consumer device. Instead, for a technology like FPGAs, becoming mainstream means establishing itself as a fundamental, widely adopted component within a diverse computing stack.
Ah, part of mix.
Exactly. Not just an optional add-on, but a core part of the system architecture in many important areas. It means becoming a go-to solution for high-growth industries. And critically, it also implies that the development tools need to become more accessible, usable by a broader pool of engineers, not just hardware specialists.
That reframes it perfectly. So the core thesis we're exploring here is that FPGAs aren't going to become a mainstream competitor to the CPU, maybe not even the GPU in all areas, but a mainstream complement.
Precisely.
Which signifies a real graduation, doesn't it? From that specialized niche to becoming a foundational pillar of what people are calling heterogeneous compute.
Yeah, and if we connect that to the bigger picture, this isn't just a technical shift. It really feels like a paradigm shift in how we think about building computing systems, which brings up the important question, what does this heterogeneous compute actually look like in practice?
Right. What is it?
Well, in essence, it's about systems that intelligently combine different types of processing units. You've got CPUs, GPUs, FPGAs, maybe even specialized ASICs or other accelerators, all working together. Each one is specifically optimized for the tasks it does best. The whole goal is to maximize the overall system performance and energy efficiency by having the right tool for each specific job, rather than trying to force one general-purpose tool to do everything, which is often inefficient.
That makes a lot of sense. A toolkit approach.
Yeah.
But Is this just a theoretical vision, or are we seeing concrete evidence? Are FPGAs actually making this shift right now on the market? What do the numbers tell us about their current trajectory?
Oh, the numbers are incredibly compelling. They really validate this shift is underway. The global FPGA market was valued at roughly USD 13.63 billion in 2024, which is already substantial.
Okay, not small.
Not small at all, but here's the kicker. It's projected to reach over USD 36 billion by 2034.
Wow, nearly triple.
Yeah, with a compound annual growth rate, a CAGR predicted to be as high as 15.2%.
That's huge growth for a hardware segment.
It really is. This isn't just steady, incremental growth. It signals a fundamental reevaluation of the FPGA's role. It's maturing beyond those traditional niche applications and becoming core infrastructure across multiple booming industries. The market isn't just getting bigger, it's getting deeper, you know? FPGAs are solving problems today that were previously outside their grasp or weren't economical.
Okay, a 15% projected KGR is massive. So where specifically are we seeing this broad and deepening adoption? Which industries are really becoming the new pillars of FPGA growth?
Yeah, this expansion is definitely being driven by some very specific end-use industries, and looking at them really highlights how FPGAs are moving into these critical mainstream roles. Take data processing, for instance. Data centers are increasingly leveraging FPGAs. They're using them to offload compute-intensive tasks, things like AI inference, high-frequency trading algorithms, and even accelerating networking functions and storage controllers.
So speeding things up in the cloud.
Exactly. For sheer speed and critically low latency in those operations, FPGAs are proving invaluable. Then there's telecommunications. Think about the massive global rollout of 5G infrastructure that demands incredible high-speed data transfer and really flexible hardware for things like baseband processing and complex beam-forming antenna arrays. FPGAs provide the adaptability needed there, especially as 5G standards continue to evolve towards 6G.
Makes sense. Standards change fast.
They do. And don't forget automotive. This is a huge one. FPGAs are becoming essential for advanced driver assistance systems, ADS, and the whole push toward autonomous vehicles. They need to handle real-time processing from multiple sensors, cameras, radar, LiDAR with very low latency. And again, they need that reconfigurability to adapt to new sensor types, evolving algorithms, and updated safety standards.
That's what for safety, yeah.
Absolutely. And finally, AI and machine learning are massive drivers right now. The just exploding demand for energy-efficient hardware acceleration for AI workloads, especially for inference at the intelligent edge. It aligns perfectly with what FPGAs offer. Their parallel processing capabilities and often better power efficiency compared to GPUs for inference tasks are key. They let AI move from the cloud right into devices, phones, cars, cameras.
Inference, not just training.
Right, inference is a big sweet spot. Geographically, we're also seeing shifts. Asia-Pacific is currently the dominant market in 2024. That's driven by its strong electronics manufacturing base and really rapid adoption of AI, ML, and IoT in countries like China, Japan, India, South Korea. But North America is also expected to see significant growth, heavily fueled by AI and IoT adoption across sectors like healthcare, finance, industrial automation, and transportation. They're integrating these advanced capabilities pretty rapidly.
So this growth isn't just about selling more chips.
Yeah.
It feels like it's about FPGAs genuinely solving increasingly complex mainstream problems across these critical high-growth industries. It really validates that shift we're talking about.
Exactly.
But how is this transition actually happening on a deeper level, like technically and developmentally? What are the key enablers that are making FPGAs more mainstream right now?
Well, the biggest one, the most profound enabler, is undoubtedly that architectural shift towards heterogeneous computing that we mentioned. It creates the need for chips like FPGAs, and we're seeing concrete examples everywhere. Cloud providers like Amazon Web Services, Microsoft Azure, they already offer virtual machine instances like AWS's F1 instances that include powerful FPGAs. Customers can rent these on demand for accelerating their specific workloads.
So it's accessible in the cloud.
Very much so. But it's even moving beyond just being a coprocessor attached to a server CPU. Take IBM's Cloud FPGA project, for example. It's exploring treating FPGAs as network-attached, sort of disaggregated resources, self-managed, remote peer processors almost, operating independently of the server CPU.
Wow, like a pool of FPGA power you can tap into.
Kind of, yeah. It signifies FPGAs potentially becoming a scalable, independent pillar of cloud infrastructure, not just an auxiliary bolted onto a CPU.
Okay, that's a big shift in thinking. What else? You mentioned AI.
Right. AI and machine learning acceleration is the second massive driver. The sheer proliferation of AI is just creating this enormous demand for specialized compute platforms. And FPGAs are uniquely positioned here, especially, as I said, for AI inference tasks, particularly out at the intelligent edge in devices, not just data centers.
Why inference specifically?
Often due to their superior power efficiency and lower latency compared to CPUs or even GPUs for many inference models. They can be reconfigured to perfectly match custom neural network topologies, which can lead to significant reductions in power consumption and execution time crucial for battery-powered devices or real-time systems. We're even seeing the chip makers respond directly. Intel, through its now standalone Altera brand, introduced Agilex FPGAs that have dedicated AI tensor blocks integrated right into the logic fabric.
So specialized AI hardware inside the FPGA.
Exactly. It's a convergence. It represents getting ASIC-like performance for certain AI functions, but retaining that crucial FPGA flexibility. It's a big deal.
Definitely sounds like it. What about actually using these things? Hasn't programming FPGAs always been notoriously difficult, requiring specialized skills?
That's historically been a major barrier, absolutely. You typically needed expertise in hardware description languages or HDLs, like VHDL or Verilog. That's often a high hurdle for software engineers.
Right, not your standard C++ or Python.
Not at all. But now we have the democratization through high-level synthesis, or HLS. This is a game changer. HLS tools allow designers to use familiar software languages, C, C++, OS, sometimes even variants of Python, to describe the desired hardware functionality. The tool then synthesizes that into the low-level HDL code.
So software folks can design hardware, basically.
It lowers the barrier significantly, yes. It dramatically shortens the time to market and makes FPGA design accessible to a much wider pool of software engineers who might need hardware acceleration but don't have deep HDL expertise. We've seen major tech companies like Microsoft using FPGAs for accelerating parts of their Bing search engine, really rely on these HLS methodologies. It's critical for deploying FPGA acceleration at scale.
HLS sounds like a massive leap forward for accessibility then. But
Yeah.
is it a perfect solution? Are there any significant trade-offs or remaining hurdles, especially when you need that absolute peak performance for high-end applications?
That's an excellent question, and yeah, it's something the industry is actively grappling with. HLS is a huge step forward, no doubt, but
Oh.
there's often still a noticeable quality of results gap, QR, they call it, between code generated automatically by HLS tools and designs that have been manually optimized by experienced HDL engineers.
Meaning the HLS version might not be as fast or efficient?
Exactly. It might use more of the FPGA's logic resources, or run at a slightly lower clock speed, or consume a bit more power compared to a hand-tuned design. For many applications, it's perfectly fine, maybe even preferable because of the faster development time. But for those really demanding high-end applications that are pushing the limits, think high-frequency trading, cutting-edge signal processing, that QRR gap can be a real drawback. So while HLS lowers the barrier to entry, it doesn't always guarantee peak optimization. There's still a place for expert HDL design.
Okay, so it helps broaden adoption, but maybe doesn't replace the specialists entirely yet? What about the tools themselves? Are we still locked into proprietary vendor ecosystems?
That's another evolving area. We're seeing the emergence of open source tool chains. The open source community has really stepped up, developing tools like Yosys for synthesis and NextPNR for place and route. These can be surprisingly capable, especially for smaller or older FPGAs, and sometimes even faster than the proprietary tools for certain tasks.
That's interesting. So could you design for any FPGA using open source?
That's the catch. While the front-end tools are getting good, a complete, fully open-source toolchain for the most complex, high-end FPGAs from, say, AMD Xilinx or Intel Altera, that remains a significant challenge. The main hurdle is the final step, generating the proprietary bitstream file that actually configures the chip's internal logic and routing. The vendors keep those formats highly proprietary and protected.
So you can design, but maybe not program the latest, biggest chips.
Largely, yes. There have been some significant achievements like reverse engineering and building an open source toolchain for a large European space-grade FPGA, which was a huge effort. But for mainstream, industrial-grade design targeting the most advanced FPGAs used in data centers, or 5G, you're still pretty much reliant on the proprietary vendor ecosystems for the full flow, especially for support and achieving maximum performance. Open source is making inroads, but it's not quite there for the highest end yet.
Got it. So, okay, the technology is evolving, the tools are improving even with some caveats, and the demand is clearly surging. This really does sound like a tectonic shift in computing. How are the big players, the semiconductor giants, actually responding to all this? What do their strategic moves tell us about the future they see for FPGAs?
Yeah, their actions, their strategic decisions, they really paint a clear picture of where things are headed. Let's start with AMD. After their huge acquisition of Xilinx, a leader in FPGAs, AMD made a very calculated move. They started discontinuing some of the older, lower-end FPGA product families, like the Spartan 2 and Spartan 3 series.
Cutting off the lower end. Wow.
It's a strategic pivot. They're streamlining their portfolio to really focus intensely on what they see as the higher value markets. That means data centers, communications infrastructure, automotive, and especially AI acceleration at the intelligent edge. They believe FPGAs offer superior power efficiency and versatility in those edge AI roles compared to competitors like, say, NVIDIA's GPUs, which are often more power hungry. AMD's strategy seems to be about combining Xilinx's leading FPGA technology with their own CPU expertise and, importantly, their modular chiplet architecture approach. They want to create these highly efficient, low-power, integrated solutions for AI inference, and they're shedding the legacy, lower-margin parts to focus resources there.
Interesting. Focusing firepower. What about Intel? They also had a major FPGA player with Altera.
Right. And Intel made a big move in early 2024. They decided to spin off their FPGA business, reestablishing it as a standalone company under the original Altera brand.
Spinning it off.
Yeah.
Why would they do that after buying it?
Well, the decision was reportedly driven by a couple of things. First, significant financial pressures within Intel itself, pushing them to streamline operations, but also a realization, perhaps, that the expected synergies between Altera's FPGA business and Intel's core CPU business hadn't fully materialized as hoped. Some analysts even felt Altera's product roadmap had kind of languished a bit under Intel's direct ownership.
So letting it be independent might actually help it.
That seems to be the strategy. Reestablishing Altera as an independent entity isn't seen as Intel retreating from the market. It's more of a strategic realignment. The goal is to give Altera greater speed, agility, and a renewed, dedicated focus on FPGA innovation. It actually signals a re-energized competitive dynamic in the high-end FPGA market, with the newly independent Altera potentially being more aggressive against AMD Xilinx.
Okay, two giants repositioning. Who else is a major player?
That brings us to Lattice Semiconductor. They've now sort of emerged as the last fully independent major manufacturer of FPGAs after the Xilinx and Altera acquisitions, and Lattice has carved out a very smart, enduring niche. Their strategy isn't to go head-to-head with the massive, high-performance, high-power flagship FPGAs from AMD and Altera. Instead, they specialize
It's socializing what?
primarily in low-power, small form factor FPGAs. They target applications in the industrial IoT space, consumer electronics, communications infrastructure, but maybe lower bandwidth parts, and certain automotive segments. Basically, the intelligent edge where power consumption and size are often more critical than raw teraflops. By doing this, Lattice effectively avoids direct competition with the big two in the highest-end markets and serves a thriving, specialized segment that still needs programmability but has different constraints.
That's a really fascinating split in strategy across the three main players. AMD focusing high, Intel spinning off Altera to refocus high, and Lattice owning the low-power niche. What's the deeper strategic meaning you see in these movements? Does this suggest like a kind of bimodal market structure for FPGAs going forward, where they aren't just one monolithic solution, but more like a tailored fabric for different needs?
Absolutely. I think bimodal is a great way to describe it. What's really fascinating is how the strategic moves of these three major vendors clearly indicate this emerging market structure. On one hand, you have this intense, high-end, high-performance battleground. That's where AMD Xilinx and the newly independent Altera are competing fiercely, primarily for sockets and data centers, for large-scale AI acceleration, high-bandwidth communications, that sort of thing. Big chips, lots of logic, high power, high price. And then on the other hand, you have this thriving, arguably just as important market for low-power, mid-range FPGAs. This is the realm of the intelligent edge, IoT, embedded systems. And that's where Lattice is strongly positioned, effectively leading that segment now. So two distinct but equally important arenas.
Exactly. And this bimodal structure isn't just about simple market segmentation. I think it suggests a future where FPGAs are viewed less as a single type of chip and more as a highly adaptable fabric, a technology that can be tailored to specific power envelopes, performance requirements, and cost constraints. It's like a strategic embrace of specialization within the FPGA world itself. And that, I believe, ensures their continued relevance and indispensability across the entire spectrum of computing needs, all the way from the massive data center down to the tiniest sensor node on the edge. They're carving out essential roles everywhere, which guarantees they'll be a staple for years to come. Okay, so bringing this all together, what does this all mean for you, the listener, trying to navigate this complex, really fast-moving tech landscape? Our deep dive today has shown, I think pretty clearly, that FPGAs aren't just some niche alternative to other computing architectures anymore. They're becoming an essential accelerator in an increasingly diverse, heterogeneous computing world. Their journey isn't about replacing CPUs or GPUs, but about occupying this newly defined, incredibly crucial space, right between the general-purpose CPU and the super-specialized fixed-function ASIC.
Yeah.
So in this heterogeneous future we've been talking about, the CPU, it probably remains the general-purpose orchestrator, right? Managing the overall system operations.
Yes, that seems likely.
The GPU will likely continue to dominate those really large-scale parallel tasks, like training massive AI models in the cloud.
Agreed. For training, they're hard to beat right now.
The ASIC, well, it remains the gold standard when you need millions of identical chips for a fixed function, where cost per unit and power efficiency are absolutely paramount.
The king of high volume, yeah.
But the FPGA, it's clearly establishing itself as the go-to solution for that vast middle ground. Applications that demand specific acceleration, better energy efficiency than a CPU maybe, lower latency than a GPU sometimes, but most critically, they need that ability to adapt and evolve after deployment, that reprogrammability.
That's the key differentiator, adaptability.
So as AI continues to proliferate, moving from the cloud out to literally billions of edge devices,
Yeah.
and as real-time performance becomes absolutely non-negotiable in critical sectors like automotive, industrial control, 5G, and beyond, the unique combination offered by FPGAs, that programmability, the potential for energy efficiency, the low latency it seems set to make them a truly mainstream, indispensable pillar of our future compute infrastructure. It feels clear, based on everything we've discussed, that FPGAs have definitely begun their journey out of the niche and into this new complementary mainstream role.
I think the evidence strongly supports that conclusion, yes.
So here's a final thought, maybe something for you to mull over. Consider how this trend towards more specialized yet adaptable hardware like FPGAs might fundamentally change the way we design everything. Not just computers, but our smart home devices, medical equipment, the very infrastructure of the internet, making it all not just faster, but potentially truly intelligent and endlessly evolving, right down at the silicon level. What kind of possibilities does that open up for future innovation? Something to think about. Thank you so much for joining us on this deep dive today. We hope you'll keep exploring.